Hello. Hello. Am I audible? Hello.
Yes, sir.
Okay. Some disturbing is my system for recording. Now it is okay. So why we are we do this thing, and the KT is your frequency. That is the frequency factor, and for calculating the KT is a different equation, and we use from actually the exclude the maximum value from your data set from this. Arranging the your we will do the when practical part, then I will show you how to, these things. So for calculating the KT, this is, see what is frequency factor and reducing very this is standard deviation when you exclude the maximum value, and generally be used for the arranging your data for the this for calculating return period Weibull equation. That is a very worldwide accepting equation, that is for sorting the your data set and calculating for the, your time period based on your probability. So overall this scenario of cheat sheet for your using Gumbel distribution for calculating the return period sorry extreme value. And this xt is a design basis extreme value for if you are using for temperature, using for wind speed or others. So this is the design value for your this things extreme value analysis. So in general way, why we are using the extreme values important for in the case of the dams or this thing. So there are two choice of this. Design the dam using the average flood. Average flood is 50 meter per second. Just assume that. Now suppose a flood of 4,000 meter cube per second occurs. The dam overflow or even fail, and it's unsafe. The choice is second choice. Design the dam using the maximum flood. Suppose that your XT is a 4,000. Then you have to design your this hydraulic structure like dam. You have to design the flood such that that's the type of the flood can bear this type of the flood effect. So maximum flood in the case of this 4,000 meter per cube. Now even during the an extreme flood, the dam safely passes the water through spillway. This is why dam engineers always study the extreme values, not average values. And some I think Rudra is telling that it's the average maximum value. It's not a average maximum value. Average maximum value we will put here, and KT is a very important factor, and this is a standard deviation. So this I will show you how to calculate it in when doing the these things practical part. Then I will show you. So the overall the first maximum flood each year. So go to the annual maximum series, then go for the this Gumbel distribution, then go for the return period fit, then for the design basis these things. Okay, this is the overall just introduction of the extreme value analysis. So how to the famous is the type 1 distribution, that is called a Gumbel distribution in hydrology. Extreme value type 1 distribution mostly used to analyze extreme events like flood peaks, maximum rainfall. This distribution was introduced by the Gumbel 1941, hence it also known as the Gumbel distribution. Following Gumbel distribution, the exceedance probability of a hydraulic logic extreme event axis collapse bar and these things 1 minus e power. This is the equation for this. And alpha beta the scale location parameter for the Gumbel's distribution. If you are from civil background, you know about these things. This is very famous. So this is the step how to be calculated, and I'm not going into deep. So how this equation has come, just in cheat sheet which I have written this, I just written here how this equation has come. Okay, so you know well about these things if you are your background is civil engineering. So the important things, this is the your Gumbel distribution equation for design basis. defining your extreme value. Yt is your here the reduced variate in return period. Y mean of the reduced variate, sample size n is your number of years or this thing, and a standard deviation or reduced variate function in the sample size n. When the sample is infinitive, that takes the infinitive, and when take the infinitive, and this value becomes this things in the case of this, and y1 and this 1.2, and this will be defined by the this uh, Gumbel had designed a table for this, and for the sample mean and for sample standard deviation. From this, for the 55, the standard deviation is this, and for the 55, the mean value, the reduced mean is this, and is the word value used, and the Gumbel had designed for this. So I'm not going to deep in this. So it is another method for this, how to step by step, which I have written here, how to calculate these things. So now I'm not going in this details. I will show you in these things better. So now next is the hydrograph. What is the hydrograph? A hydrograph is that shows how river discharge flow at a particular point change with time, usually during the and after a rainfall or a storm. Hydrograph is like a heartbeat of a river. This is very important. It shows how fast and how much the river responds on a river over time. Hydrographs represent the flow, that is the discharge versus time. So hydrographs help us understand how a catchment or basin respond to rainfall, estimate peak discharge, lag time and flood duration, design drainage system, dams and flood control structure. So this graph, this is called a hydrograph, and in x-axis this is your time, and y-axis is your runoff or oblique discharge cubic meter. So when we plot the stream flow after a rainstorm, or the hydrograph usually has three parts: rising limb, this is the rising limb, and this portion is a peak discharge, and is the falling limb, and this is your this what is called storm runoff type, and this is your normal base, and A is your approach segments starting from this, and this is the peak rainfall, and this is your lag time, and this will be more clear when we are going to the a simple example. And this is a very simple example. A hydrograph is the river heartbeat and the catchment fingerprint. Catchment, you know about this thing, na? Can anyone tell me about the catchment?
The area of land draining into a stream is called catchment.
Yes, catchment is also called a drainage basin or watershed. It is an area of a
Yes,
land
sir.
where the all rainwater flows to a common outlet, such as a river, lake, reservoir, or dam. Okay, this is the catchment. So imagine it rains heavily on your area. Rain starts at 2 p.m. Okay, and and in your area is a river. Suppose assume that in a river, due to this rainfall, after 1 hour at 3 p.m. the river start to rise at 3 p.m. This is the rising limb. Exactly this thing is a rising limb. So after starting the rainfall, after 1 hour, the elevation of your surface elevation of your river is rising. That is called the rising limb. Rainwater reaching the river flows become highest at 6 p.m. That is your peak. This is the peak discharge. At this is the peak when the rainfall is at a maximum. So this peak discharge, maximum flood is occurred. After that, the flow slowly decreases and comes back to the normal at 12 meters. This is your called these things falling limb. So this tell you every catchment drainage area has a unique hydrograph shape. A small and steep catchment, it means the sharp and quick peak, fast response, and a large flat catchment is slow, broad, and peak, so slow response. So just see different type of the catchment. So if the outlet is from here to here, so the rising limb is just so the your positive skid, and this is from here to here, then so the negative skid, and here the two limbs are there. Here the one is the here, is the one is the here. What is the meaning of this, statistical meaning of this? Can anyone tell me why this for this catchment we got the two rising limb peak discharge here? 1 2 in, but in this case 1 1 only. Can anyone explain it? Hello? Hydro, these are the hydrograph, okay? For this A catchment this hydrograph, for B catchment this hydrograph. Just see if opposite the outlet points, and in this case just see that the your shape of your this hydrograph has changed, okay? But in this case the hydrographs showing the two peak discharge. Why it is showing, can anyone explain this? What is the statistical meaning of this? Because hydrographs is the heartbeat of your catchment area. You can only draw the your catchment area just based on this. If someone shows you a positive skid, then you can assume that the river passing from here to here. If it someone the negative skid, then you can assume that the river passing from here to here. Okay, just see that the outlet point is just opposite to this thing. But what is the meaning of this? For C, you oftenly see have this A and B structure, but see what about the C, meaning of the C. Why this is occur two peak discharge? Can anyone explain this? Hello, am I audible? Hello, hello. Hel
Yes.
yes, Pito, can you explain
Yep.
this? Explain this. Why this graph showing the two peak discharge for C hydrograph? Can you explain this? Or Prasant, can you explain this?
See. Sorry, I cannot explain that.
Okay, okay, no problem. So here just see, here the only one the catchment area, here the B is the only one but it's domaining part. This is your domain. Here the two domains, two sets of the data are occurred. Here the domain 1 and domain 2. So for this, rainfall is just varying from here to here. That's why here the
Mm-hmm.
peak discharge is different for this area, this peak discharge, and this showing the this type of the shape. So that's why B occurred the two. And whenever you found in a statistical analysis in a graphical representation of your this type of the graph, that is skewed and normal distribution type of graph, and this is basically skewed, and so the two domains, it represent always the data nature has changed from here to it. Of course the data nature has, and this is the for the very large for the catchment area. So here the rainfall intensity is different, here the rainfall intensity is different. So peak occur two types of the peaks occur. So geographically, geologically, area is changed. So that's why the hydrograph, this is basically called the hydrograph, and it's the heartbeat of your the catchment area. So hydrograph is a graph that shows the how river discharge change with the time. This is the basic things. So hydrograph tells the how much water is falling at different times. So x-axis is your time and y-axis is discharge flow rate. Imagine if there is no type of the rain, so the river imagine if there is no rain, then the hydrograph how looks like. Can anyone tell me? This is the skewed type of the graph. Positive, of course, is the positive skewed because it is increasing with the time. Here the hums are here and its tails are here. This is negative skewed, and this is your to mix up the two data set for the rainfall intensity bearing with. If rainfall is not occurred in a catchment area, this is without rainfall data. We will similarly river data, here the stream discharge and time, be just these things. Then what will happen? Then this show the normal distribution type, a bell-shaped curve, because it's showing the symmetrical distribution for both sides, from this side and this side. So this is the this tells you the graph how the rainfall is changing with time, and if not rainfall occur, then river discharge, showing the lots of things about this. So I think this will be clear to all of you.
Yes, sir.
So basics of hydraulic modeling. Now come to the hydraulic modeling of this. So there are three types of the modeling, basically four types of the modeling. The first is 1D modeling, second is 2D modeling, and the coupling of 1D, 2D, and next is the 3D modeling. So we can say that these are three types of modeling. So 1D, that is one dimensional, water flows in one direction like along a river or drain, which was used when modeling flow in a straight channel or pipe. Faster results with less data. Limitation does not show where water spreads sideways during floods. So 2D dimensional, water spreads in two directions, forward and sideways. Urban flooding or flood floods see exactly where the water will go, more time and computer power, but gives more detail. And the third one is the 3D modeling, the three dimensional. Water is the model in a x, y, and up down z direction. It simulates the turbulence wave and vertical flow you use when dam breaks, coastal flows, and engineering structures and heavy data mostly using this. So next is the question, what is the hydraulic modeling? Hydraulic modeling is a mathematical or physical representation of water movement within a system such as river, lakes, pipelines, or drainage network. So hydraulic modeling is a frequently used to understand a hydraulic system's behavior under different scenario at a different spatial and temporal scales. In simple terms, it helps us simulate how water flows, rises, and behaves under different conditions like rainfall, dam release, or flood event. Example, this is a lab experiment. We can experiment in lab and create a just natural scenario for the flooding events or dam breaching events, and calculate the and observe the wave behavior. And the second one is the your this is the after this is a higher cost and time consuming because we have to use area required and set up these things. And now next is the modeling. So modeling is a less time required and cost is also less, but scaled down physical setup built in a laboratory, example flume tank channel to simulate real world hydraulic condition, so the flow velocity on for the hydraulic modeling. So this modeling is a computer based simulation using mathematical equation like sand equation used in the HECRAS, and to represent fluid flow in and hydraulic behavior. So different types of the hydraulic modeling is flow is considered one dimensional and 1D both in channel and floodplains. Flow is considered two dimensional in both channel, and flow is 1D, 2D, and flow is 3D, which you have explained this. So along only channel path, cut the one dimension. So it's done by the HECRAS, Mike 11. So that's why Mike 11 see the 1D modeling is this. Uh, Here the example SWMM, which have in the first slide, storm and water management model software. Two dimensional assume flow in a two direction, longitudinal and lateral, and this along the bank and along the river bed. And two flow is a very good software for this type of the modeling, but HECRAS is also good, and Mike is also good. Coupled up this, you can also do this type of the modeling in your HECRAS. And 3D modeling, for 3D only depth and flow 3D is done for this till now, and it's a paid software and very costly software. So we are in for 1D and 2D with the HECRAS model, and HECRAS is good for the industrial use. Many of the industries are using the HECRAS, so we will work on. So concept for 1D hard modeling, and the governing is the Sand-Bennett equation. And what is the Sand-Bennett equation? We'll see. Flowing along a single path channel crossing the flow, and 2D for the flow over a surface floodplain, and 2D Sand-Bennett solo water equation, and this governing equation for this. And for the 3D, it's not Sand-Bennett equation; it's a full 3D Naber-Stokes equation. So computation cost for 1D is low, medium to high, and very high computation for the 3D. So pros and cons we will see. First, simple, good for bulk flow, effective, and cons is the limited spatial details, poor for spreading this thing. Computationally intensive, can struggle with complex inner channel structure. complex setup, calibration can be intricate, extremely high cost, data intensive, not for large areas. Okay, these are, I'm not going to read this thing, just for the information purpose I have so told you. So introduction to Hecra sort of hydraulic modeling. So we will do the first these things, Hecra's modeling, tomorrow at 12 p.m. And I will stop here. And before stopping this, I want to know from your side, what is the rating curve? Because I'm just telling the many times of this. What is the rating curve? Can anyone explain this?
It is
And
a graphical representation of discharge versus stage.
discharge versus the
Stage.
that's fine. Okay. That's the rating curve is different. Discharge with the this for calculating the peak distance. Here just give me the this pen. Okay. This is your runoff. Here the runoff, and this is the discharge. So this rating curve is calculating for your peak discharge method, which we have seen the rational method one. Now in HECRAS we will use the stage. Stage means a different elevation. Here the difference elevation, and here the discharge. If we have the data, then we will use this type of the curve in our HECRAS. So can now next thing is the, I want to know from your side, what is the flood routing? Because flood routing is a very important terminology in the flood modeling. Can anyone explain it? After then I will stop here and we will go for the some modeling work, some GIS processing modeling work. Time is very less. If no, don't know, then I will explain it. Tomorrow we will do work on the 1D for real data and dummy data, and we will see the different scenario for the pipe, canal, and others, how behaves these things, and whether my model is accurate or not. We'll see in a different scenario. But before this is stopping, I want to know from your side, what is the flood routing? Can anyone explain this? Rudra? Rudra is here. Hello, Prasant. Can you tell me? Or
Flood
Jayashree?
routing is carried out in a reservoir to determine the maximum rise in water surface
Hmm.
and discharge in downstream channel
Mm-hmm.
when particular flood pass through it.
Okay, nice. But can you explain for the flood routing for the your HECRAS and HECHMS? In both there is something difference between the these things. For
No, no.
HECHMS, we will take the different equation, and for HECRAS, we will take the different equation. So I will explain it very quickly. What is the flood routing? Flood routing is a process of tracking and predicting how a flood wave changes as it travels through a river channel or reservoir over time, as you explained this thing. So when a flood moves downstream, it doesn't not keep the same shape or discharge due to storage, channel resistance, frictions, and channel slope and flow velocity. The flood wave gradually changes. So at the peak stage and the falling stage, there should be changes in the graph. So how much will the peak discharge decrease, and how much will the time will the flood take to each downstream location, and how will the shape of the hydrograph change, and what will be the water level and discharge at a different location. And this terminology comes under the flood routing. In simple words, flood routing is the process of predicting how flood wave moves and changes from one location to another location. So why does the flood wave change? First is the storage effect. Some flood water is temporarily stored in a within the river channel and floodplains. More storage means lower flood peak and longer flood duration. Okay. And the second one is the friction effect. Water loss energy due to friction with river bed, river, as we have seen in the this responsible for the your manning coefficient, floodplains, vegetation. And the third one is the channel slope. A steeper river allows water move to faster, steep slope faster movement, and flat slope slower movement. And the fourth one is the very important, that is the channel geometry. The width, depth, and shape of the river also affect the how the flood travels, and narrow river behaves different from a wider. So, what is the objective of the flood routing? The main objective are the predicting downstream flood discharge, estimate peak discharge, calculate flood travel time, estimate water surface elevation, prepare flood inundation map, and support flood forecasting and early warning system. So these are the things which we will see in this. And can anyone explain the how many types of the flood routing? How many types?
There are generally two types,
Yeah,
lump routing and hydrological routing.
yes, just but in a learning word in a very simple word, flood routing is divided into two major categories. The first is reservoir routing. That called the reservoir routing studies the movement of flood water through a reservoir used for reservoir dams and lakes, and that's done by the your HECRAS. In reservoir routing, the inflow hydrograph enters the reservoir, some water set is stored, and the remaining water leaves as the outflow. The outflow hydrograph is usually smaller and delayed. Of course, and most common method is used for this reservoir. If you are not using for a dam and these things, suppose that you are using only for the reservoir. So most common in hack HMS, that's the equation in a modified plus method. In modified plus method, very simple. In enter water and output water, I minus O. The, equation only use thing. And second one is channel routing. Channel routing is studies the movement of flood water through river and canals used for river, stream, channel, drainage channel. And these are the and the popular methods include the Mussingum method, Mussingum Kunj method, kinematic wave diffusion method, and in this case the Mussingum method is very popular for in HECRAS. In HEC HMS, that is the your modified plus method. That's called the modified plus method, and Mussingum or this Massingham method is defined as not Massingham modified plus method is I minus O and ds by dt, only ds by dt with time, and s is the your storage, and ds by dt is the rate of change of the storage. I is the inflow, I minus O, and O is your outflow, meaning that water entering minus water leaving change in storage. That is only concept used in the hack HMS. But in HECRAS, it is used for the Massingham method. And Massingham method, you know that is a very uh, complex method. So, and you know difference between the hack HMS and HECRAS. One is the hydrologic and other one is the hydraulic. Which one is the hydrologic and which one is the hydraulic? Can anyone tell me about this thing?
HMS is hydrological modeling, and
Yeah.
HRS is hydraulic modeling.
Yes, yes, absolutely correct. And why we called it the hydrologic hack HMS, and why we called it the HECRAS is the hydraulic?
In HMS, we will find out rainfall data
Hmm.
and रन ऑफ डाटा,
Oh,
या इस तरीके से कह सकते हैं कि
yes.
रेनफॉल डाटा एंड रन ऑफ डाटा के ऊपर वर्क करते हैं.
Yes, that you can say that, but it's have a limitation. But in HECRAS, hydraulic have a not limitation. It depends on the time dependent, but hydrologic is not a time dependent. Okay, that's the difference between the. So powerful, of course, the powerful is the HECRAS in comparison to HEC HMS. So for runfall modeling and surface runoff modeling, HEC HMS is good, but for in a deeper for the your dam break analysis, if you're doing in this HEC HMS, then it's limited. But it's in a HECRAS, it's excellent. And HEC HMS use only the modifier plus in, and this equation is the Massingham and alag methods. And HECRAS is used for the river flow simulation method, but it's this main purpose for the use for a HMS rain runoff modeling. So these are the difference between things, and I will stop here and go for the some modeling geoprocessing GIS modeling for today's session, because it's already done 8:49. And brief introduction, I want to give you the brief introduction about the this QGIS and other software. because the agenda I have to cover this. So I just close it. Uh, Okay, 62 slides. I will just quick. I want to just show you the brief introduction about the GIS, because yesterday I gave you the brief introduction about the Python. So I want to here give you the what is the DM file, raster vector files, what is these are. So this will be helpful for your modeling purpose. Recording is going on okay, recording is going on. So my screen is visible to all of you. Is it visible?
Yes, sir.
Yes, sir.
Okay. So quick, what is GIS? Can anyone explain what is the GIS? Hello, can anyone explain it? What is GIS? GIS is nothing.
GIS is a software. With the help of GIS, we can analyze and interpret data.
Okay, that's why I'm asking the question, what is the GIS? Whenever you talk about a GIS, in your mind, software computer has come, but it doesn't mean that it's not related. In ancient time, we prepared the maps and these things without help of the software, but of course the method is very tedious. So GIS is a technology that used to create, manage, analyze and map all types of the data. That is the GIS. GIS connected data to a map, integrating location data where things are with all types of descriptive information, what things are like there. This provides a foundation for mapping and analysis that is used in science and almost every industries. So GIS nowadays it is using for your things, that is computer software and programming and other. So why we need GIS? GIS is like a smart map that helps us, and everyone know about the why we need the GIS. So I'm not going to this deep. So the first is with the help of the GIS, these are satellite pictures, and we do the some work on the GIS, and then see that with the time the image of this water body has vanished from here to here. So this is the very easy way we can observe and visualize the things, and that's is the part of the GIS things. So this is another example for GIS. What does GIS do? Data management, mapping and visualization, spatial analysis, and communication skill. And how GIS can work? Use choosing the right location. This is the three maps, and see how in animated is locate your potential store for reaching the in a particular with the help of the GIS and this selected store. Next is the same example is this. You can see in this finding the best route and keeping the tracking of this. So how the just show you the in emergency case how to maintenance the road and these things. You can see that this with the help of this, and these images are available on the ISRI. So you can. So I'm not going to the deep. Just my aim is to give you the brief introduction about the DM model and other vectors and raster and planning future for this, and yes also emergency planning. This is a cyclone and how much time will hit on this coastal region and how affected area we can simulate in lab like HECRAS and this thing. HECRAS is also a GIS software but with a simulation feature. So 40 practical GIS research and project in hydrology land use research is a practical use. So basic concept of GIS and these things I'm not going into. So rasters, come to the this thing raster. So can anyone explain the what is a raster? So okay, I will explain. The raster are made up of the matrix of pixels, also called the cells, each containing a value that represent the condition for the area covered by the at cell. A raster that is composed of rows running and columns running a pixel, and this is your raster, and this a single box is called the pixel. So there is a difference between a cell and pixel. You cannot say about this is the cell, this is the pixel. Every pixel is a cell, but every cell is not a pixel. So a raster is comprised of rows and running and columns. A pixel, also known as cells. Every pixel is a cell, but every cell is not a pixel. Each pixel represents a geographical region, and that the values is that pixel represent the some characteristics of the region. Each pixel has a value representing something about the specific area, like temperature, color, or elevation. Both cells and pixel refer to the smallest unit of the information in a raster dataset. Pixel is an abbreviation of picture element and often used when the describing an imaginary, whereas cell is often used for when describing raster data. Cell pixel and dimension and value. Pixels and images. Pixel sort picture element. This term is used mostly for imaginary and visualization. Cell, this term is used for raster data and refers to the same concept as a pixel. So when you're seeing my screen and its skin is colorful and this, so every it makes a very small dot. That small dot is called the pixel. Okay, so pixel is your picture element and cell is your raster element, but both are the smallest element of your. So dimension of the both pixel and cells have the same size, defining the area of these things. So temperature, showing these things, soil type, and these are the example for this. So bands, you know about the bands and these things, bit width things. Okay, I will explain it later, but I want to do go to the some practical part of this. So because time is very less, I already 9 p.m. is done. So lots of the theories are available this thing. So the first things why I'm showing you in this okay, the in a QGIS, you know about the QGIS software.
Yes, sir.
Okay, so then fine. If you know about the QGIS, so it is a practical, it's a open access software. So you can find in anywhere on the internet. And I have shared also its your latest version of the your setup file. If you cannot download the from internet, so use this thing. So installation process I have written here. I'm not going to this thing. So I'm go and this looks like here. If you know about these things or know you know about this interface, what is this do? I will share with. I have already shared this thing with you, so you can do. Now my purpose is do. I want to do this operation in the QGIS. That is the buffer, clip, intersect, union, erase, merge, and dissolve special join. So the first open the QGIS. Hello. Yes, Safar, you want to say something? Mohammed Safar, you want to say something? Because I am just
Yes,
seeing
sure.
what? Please ask. Hello. Please ask if you want to say something. Okay, so these are the operation within the one by one. We will see the quick. The first is the buffer. You know how to draw a buffer line. So for buffer line, when you want, the first is just here go to the layer, add layer, and go for the no create layer and new save file, and create here the save file name is suppose that in desktop in one. Here I'm giving the name is this ERT, just for given now ERT, and select this point, and this is your WGS84. Take the any 45 unit, okay, and do it. Okay, now do it here on the toggle editor and mark. Take select this and mark here. Just give the attribute one and this thing. Now save toggle editor. Now save this, zoom to layer. Mm, okay, what happened to my uh, how to install the plugin? When you click on this plugin and go here, then a plugin section will open and search here and you can install this tab. And the one plugin name is SCM GIS. So this is used for the base map for this. Suppose that I'm open this, so this type of the map will. I'm from India, so here, and I'm going to mark randomly points here. Suppose that this is your thing. So layer, add layer, and just create layer, new save file. Okay, and just make it one, give it 1 to 12 numbers, dot shp, dot shp. mm, give its point geometry and give its UTM projection. Suppose that 45n. I'm just for the this. Now this has been done. Now this is the toggle editor. On this and select the any point. Not randomly. I think this 45n is I think here. So for this right here the any number ID 12 I have just written. See, it has done. Now of this and save. Now search in here the processing tool, processing tool, search here and write here the buffer. So when you click on the geometry, vector geometry buffer, and this type 12 and the meters and kilometers, so 10 meters buffer I want to make. So run it and see, uh, buffer has done for 10 meter. Of course this is very small. When you click on this and here, so this buffer is you can measure it its radius from here. See, almost the 10 meter is this. So one has done. Now next is your another things, just remove it. Second is your buffer has done clip feature. So I have just prepared the data set for you and just do it and try to this is, there are two types of clip, that is vector clip and this things, what's name is this raster clip. So take the extension of SHP, here the map for geology map, and here the uh, buffer things. So just select it and drag and drop in your. Okay, this is a geology for the particular area, and this is your buffer. So change the buffer color, then you will look much better than this. I think make it the green color. Okay, apply, or you can make it the this transparent. Okay, red color will. Okay, the light green color will. Okay, now we want to clip this thing. So clip this. Just search here the clip and go here the input layer. Input layer is your raster layer. Sorry, why this is your input your this layer, this geology map, and extend up to, sorry, this is clip. Okay. Okay, now this is the geology. This is the buffer by mask layer, and run it, and its projection must be the same. Okay, then when you parameter do not use the all the same CRS. Okay, projection is a different, that's why it is showing the different but geology or buffer projection is different. That's why when this just remove it and see, this is your clipping feature of your geology for this. This is the one way for the doing the processing for this. Necessary intersect and these things. So I'm not going to in a big detail things here. I just if you see my this day 2, I just write the all the methodology of this and a data set I have given you, which I have shared by your this email. So just do it and try it and read these things, and this is the assignment for you, how to open and this thing, because this is a very easy way and everyone know about these things, and must read about my PPT for this, for UTM projection, what is the UTM projection, and what is the DM and spatial data, how many types of the save file, and which I have written here, save file .ssp.kml files. This is important for this, so read it, all these things. And I'm going to stop here, and this is the assignment for your do the practical in this thing, because this is the very basic things. Okay, so I'm going to stop here. So today, I hope today class is not so boring class. So if you have any questions, any doubt, please ask. Hello. Hello.
Hello.
Yes, am I audible? Yes, yes, speak.
Thank you, sir.
Okay, if you have any question, please ask through WhatsApp and chat. And how is the today class? Please give the feedback for this. Okay.
Mhm.
Yes, Tahir Wani, second half will be hands-on. Don't worry, because theory is very important. And from tomorrow, theory will going on. Practical will going on. Only practical session is remaining. So don't worry about this thing. So, Peto, bye bye. Good night.
Yeah, see you. Good night.